Hi, welcome to the analysis and design of a flyback converter. This is part 22. What I'm going to be covering, which I haven't covered on the previous videos, is the output capacitor value, how to select it, and what specifications you would be concerned that would let you pick the correct capacitor value that will get you the specification. Okay, so typically you're gonna have a ripple specification. Okay, that's one of the probably the most important. They'll give you a specification, and once you have the specification and you know how much you will be designing, you have to know how the ESR of the capacitor, which is this. In case you don't know what ESR means, it's equivalent series resistor or resistance. Okay. So basically all capacitors have the capacitance, and then you have a resistor. ESR. SR. And in some cases, if you have long leads, you might even have equivalent series inductance. I'll just put a little L for inductor. Okay. So basically, but typically if you're using surface mounts, you can kind of neglect this, or you say that it's very small, and especially for the frequencies that we're operating, which is 100 kilohertz, the series inductance is not too critical. Okay, and then once you have that and understand that, then we'll see if we can select the proper capacitance. Okay, so again, I will reiterate that the most important is the upward ripple. Okay, and what is the upward ripple? Okay, well, if you were, let's say you have a power supply, and I'm just going to model it as a voltage source. Okay, and if you connect your scope to it, and let's say this is 12 volts, well, you should have, and let me change this a little bit. Let's say you have a 12 volt supply. Well, theoretically you should have 12 volts. Okay, or at least the average would be 12 volts, but then you'll have a little bit of a peak and valley, and this maximum, you may have a voltage where it may go to 12.1 volts, and it may go down to 11.9 volts. Okay, so you have this where it's going up and down, up and down. Okay, well, this delta in voltage is your ripple voltage. Okay, now keep in mind this blue line is the average voltage. Okay, you can also consider that as your DC output voltage, and you can consider the ripple current, this current that you see here, that's the current right there. You can consider it as AC current, so you can say that it's I ripple. you can think of it as the AC component, and this average is the DC. Okay, so by definition, the ripple in this case is going to be the difference between the peak or the maximum. This is the max, and this would be the min. Okay, so in this case it would be 12.1 minus 11.9, so you'll have a approximately 0.2 or 200 millivolts peak to peak, since you're reading from this peak, which is the maximum peak, to the minimum peak. Okay, so here's some typical specifications that I've seen. And typical that I've seen is less than or equal to 1% of the output voltage. Okay, so if you have a 5-volt supply, then that would translate to 50 millivolts. If you have a 3.3, then it would be 33 millivolts. Okay, so if you have a 12 volt, it would be 120 millivolts, but since 120 millivolts is higher than the 50, then we'll go ahead and bring this down to 50 millivolts. And this is what I'm going to be using in our example. Okay, so how do you calculate the ripple? This is kind of like a back of the envelope or rule of thumb. Okay, so basically this is your flyback. Okay, the primary, the current will look like this. Okay, and that will be going through here. And this typically happens when the MOSFET is on. And let me say that this is I pri. Okay. And when the MOSFET turns off, then the secondary flies up, and you have something like that. So this would be I secondary. And remember, this current is flowing through here. I sec. Okay, so this is what it looks like. Okay, now if you take the average, again, there's a little bit of a relationship that if you take the average, and here's a big assumption. This is assuming that if, I'm going to put a big star here, assuming that it's 50% duty cycle, then you can use a very simple formula or rule of thumb. Okay, let me go ahead and move this. You can use this formula. If you know what the primary peak is, you can divide it by the turns ratio. That will get you a quick answer. But you can also use this. You can say that the current output, and I'll put IO times 4. Okay, so what do I mean by that? Well, if this IO, this is IO, and you can also think of this as I DC. Okay, in our example, I'm using a IDC, a 1 amp. Okay, so basically the average would look here, will be 1 amp. Therefore, this peak current is going to be 4 times that. In other words, if this is 0 right here, it means that the current right there is going to be 4 amps peak. Okay. So this is that. Now remember, here during this node you have both the IDC, which is this, and you have your IAC, which is the ripple, which is IAC. Okay, so the DC actually flows in this direction. You can kind of think of it that way. And the AC, typically, since it's frequency dependent, will flow through the least impedance, and typically you want it to flow right here. Okay, so it'll make a little sense in a little bit. Okay, so you have that. Okay. So let's look at an example. Okay, like I said, we're going to use 12 volts. I out is 1 amp, and we want to design or select the capacitors where we get 50 millivolts or less. Okay, so based in that this is 1 amp, I already said that the peak is going to be 4 amps. Okay, got that. Okay, so now we're going to go ahead and do a little bit of numbers. Since it's 12 volts, 1 amps, that means this is going to be 12 ohms. Okay, and let me make sure that this is labeled correct. Okay, so you have this current, this ripple, AC current, and the AC current typically will try to flow in the impedance or the lowest impedance. Okay, so you have this impedance looking through this, which is the capacitor and the ESR, and then you also have this impedance, which is just your load. In this case, it's 12 ohms. Okay, so if we go ahead, change this and say this is Zn, and then we'll say this is Z load, just to be a little bit more specific. Okay, so we're going to say that the impedance looking in this branch is the ESR plus the capacitance reactance of the capacitor. Okay, and in this case I just put plus for the time being. Okay, and if you use phasor notation, you know that that would be a negative, and since it's a negative, an imaginary, and since it's a capacitor, it actually takes a negative value, and you can add the imaginary here. So basically the impedance is going to be a real part, which is the ESR, and then you have the capacitor. Okay. So that's what you gotta work with. In other words, that you have basically two components. Okay. And actually this is how you calculate or how you set your ripple. Okay. So basically the ripple, if it's designed properly, is going to be dependent on this AC or the I peak. And again, you can say the I peak, in this case, you can think of it as the IAC. Okay. And it's going to be multiplied by the impedance combination of the ESR and the capacitor. So this is what I'm saying right here. So here's the Zn, and then I'll say that I peak. Or you can also say that it's IAC. Another name, hopefully you can say I ripple. So they're all kind of interchangeable. I ripple, IAC, and I peak. I'm referring to this waveform. Okay. So if you look at the equation, if you want this small, right? If you want R ripple small, which is the intent, if you look at the equation, that means that you want to make the ESR small, right? So you want the ESR small. So when the ESR goes small, the ripple gets smaller. But the same token, if you look in here, okay, this is a capacitance. Okay, here's the capacitance CO. So you also want all of this term small. And in order to make this small, you need to make the capacitor big. So in this case, the capacitor, you want it big. Okay. That way the X of C, which is what this is X of C, is small. Okay, so that's the main idea. Okay, you want to make the capacitor as big as possible in the ESR. Okay, so you might say, well, how small? Okay, and how do we start? Okay, so let's go ahead and start, and let me move this a little bit. Okay, go ahead and erase this. Let's start with the ripple specification. Okay, in this case we want something 50 millivolts or smaller. Okay, so you can think in terms of this. You can say that the impedance, well, hang on, let me backtrack again. We said that the ripple is the I peak or the AC times the impedance. Okay, so then by the same token, then now we can say the impedance is V ripple divided by your I peak. Okay, so if that's the case, then you can say, you can try and calculate, okay, what kind of impedance do I need? Okay, So you can say that it's 0.05 volts. It's 50 millivolts divided by 4 amps peak, which is the AC. Okay, so you can 0.05 divided by 4, so you come out with 12 milliohms. Okay, so basically you want the impedance, the capacitor, and the ESR. You want the equivalent impedance between here and here to be 12.5 milliohms or less. Okay. So here's two methods of selecting the capacitance value, and we're going to use a well-known equation. This is the equation that describes a capacitor, which is CO and dV dt. So this dV dt or dV, this is going to be your 50 millivolts. Okay, and the time, assuming that it's 50% duty cycle, and we have 100 kilohertz as the frequency, so that gives you a T on of 5 microseconds. Okay, so that would be your dt, and when you plug in the equation and solve for C, I get 100 microfarads. Okay, now mind you, this is just the impedance of the capacitor, or at least the capacitor will give you this delta of 50. Okay, and now you have to remember that the capacitor always has an ESR, and we haven't accounted for that yet. Okay, so that's the first method. You can use that equation. Okay, another method is, since we've already calculated what the impedance is, okay, then we can use the capacitance reactance of the capacitor. Okay, typically this reactance would look, the reactance capacitance formula looks like this. Okay, so in this case we know that this value is 12.5 milliohms. Okay, so if we switch these around, okay, in other words, bring C out over here and bring this over here. Let me show this a little bit more. Okay, so we can basically solve for CO. Okay, this is X of C, and we've already calculated here that we needed 12.5, so we can say 2 pi 100 kilohertz times 12.5 milliohms. Okay, and I've already calculated, but let me just be sure, verify and check. 6.28 times 100 times 0.0125 close, and I get 127 microfarads. Okay, so if you notice, these two equations are pretty close. Okay, so what does this mean? it means that this is the minimum. Okay, minimum capacitance. So it should be bigger than this. Okay, bigger. Okay, so let's simulate that. Okay, so let's go ahead and in this case I'm gonna go ahead, instead of using 100, I'm gonna up it up, go 126. Okay, so here is, okay, now this is assuming, and what I'm gonna do is I'm gonna take the ESR off and just put a capacitor here. Okay, so I should have 12 volts coming out of here, and I should have one amp going through this load resistor. This load resistor is defined here, 12 ohms, and the 12 or the 4 amps peak should be going through this capacitor. So I press run. Okay. Let me change this. Okay. So here, this is the ripple current. If you notice, this is blue. It's the current through D4. That's the current going through D4. That current goes through C1. And just to be sure, I can plot the current through C1. Okay, let me go ahead and add that, but it's going to be inverted. So it should be two. Okay, so here delta is 4. From here to here is 4 amps. Okay, but that's being represented, it's the same current going through the diode. Okay, so I'm going to go ahead and remove it, but I just want to show that it's that current is going through the current going through the diode is going through the capacitor. So go ahead and I'll delete it. Okay, and the average current is I4. Okay, I4 is the current going through your load resistor. Okay, so now let's measure the peak to peak. Okay, so in this case, here's the output voltage, here's the maximum, and here's the minimum. Okay, so we go here. Here's the delta. Put a cursor here. Put a cursor here. And not sure if you can see it right there. 44.9 millivolts. So it's from here to here. Okay. So it's pretty close in agreement to what we calculated. Okay. So that proves that this equations will give you the absolute minimum. But the problem is all capacitors have a ESR associated. Okay, and that ESR will add ripple and will generally dominate the ripple. So I'm going to go ahead and make a statement here, and we're going to say that the ESR sets the ripple, provided that CO is big. Okay, so let's let's take a look how the ESR affects it. Okay, so I'm going to go ahead and add a resistor. Okay, so we were talking that the impedance of this is 12, approximately 12.4, no, 12.5 milli. Let's make this 25 milliohms. Okay, and before we do that, let's see if we can calculate how that affects us. Okay. Oops, excuse me. So now we have, okay, Zn. So we have 127 microfarads, which is equivalent to 12.5 milliohms imaginary. Okay, and then we added a ESR that is 25 milliohms. Okay, so I had mentioned that the ripple is going to be I ripple times the impedance. Okay, so we know that this is 4 amps. Okay, so now this is where, now to find the impedance of this network, we get the square root of the real, which is 25 milliohms, squared, plus the impedance of this term, we have the capacitor, which is 25 milliohms, squared. Okay, so let's see what we get. So I'm going to go parentheses point, I'm sorry, let me redo it, parentheses 0.025 squared plus 0.0125 squared, close parentheses, raised to 0.5. 27.9 milliohms. Okay, so that's the impedance. Okay, so now we can multiply that times 4 amps. So we should have a ripple close to or approximate to 111 millivolts. So in this case, not meet spec. Okay, so let's see how close. Okay, run it. Okay, let's see the approximate. How close is it? Okay, So here says that the ripple is 103 millivolts. Remember, it used to be 50, but now because I added a resistor, it's 103 millivolts, and I calculated that it would be 110 millivolts. So this is very close to simulation. Simulation's at 103 millivolts, or say that it's SPICE. Okay. So now you see how the effect that as this gets bigger, your ripple is going to get bigger. Okay. So what do you do? Okay. And what would be the practical? Okay. So you have to select capacitors that will give you the spec or your specification. Okay, here's a website. This is a Chemet website, and here's various capacitors. Okay, and this, let me see, there's a X size, and since we're going to be powering 12 volts, we double the voltage. Okay, so we get a 25. So in this case, you can get up to a 68. Okay, so let's click on that. Okay, so then you come here, and this is the switching frequency that we're operating at 100 kilohertz. Okay, so now it's 100. If you notice, there's two capacitors with a approximately close to 45. So basically this is a 45 ohm. I'm sorry, it's a 68 ohm. I'm sorry, 68 microfarad with a, let's pick the largest one, 45. Okay, 45. Okay, so this is would be the equivalent of that capacitor. Okay, and you'll notice the impedance is still too high. Okay, the ripple's still going to be too high. Remember, we wanted 12. Okay, the ripple right now is 184. Okay, so we can work with that. Okay, so let's go back. Let's make our notes. So there's a T510 capacitor at 25 volts that is 68 microfarad, and it has 45 milli ohms. Okay, this value is pretty close to what we had calculated of 100 or 125. Okay, and remember, we want an impedance of 12 or less. Okay, so we want the impedance of 12.5. Okay, so let's give ourselves margin. Let's shoot. Let's set this to maybe 8 milliohms. Okay, so we can say this, that the impedance in this case is going to be 8 milliohms ESR and the number. Okay, so then by that token we can say how many capacitors do we need. Okay, so in this case it's a 45 milliohm and we want 8 milliohm. Okay, so we can say 45 divided by 8. So we need at least 5. Let's run it down to 5. It's 5.6. Let's say 5. Okay. So, and so this is why you see a bunch of capacitors hooked up in parallel. Basically, they're paralleling the capacitors so they can get a low enough ESR. Okay, so let's move that there. Okay. Another one. 2, 3, one more. 4, 5. Okay. So you'll see that it is not uncommon, or rather it's very common to see a whole bank of capacitors, and this is why. Okay. Okay, so before we do, let's examine, let's see what we have. Okay, so basically we've connected 5, 1, 2, 3, 4, 1, 2, 3, 4, 5. This is what we have. Okay, and these are 68, 68, 68, 68, 68, and I believe this is 45, 45, 45, 45, 45. Okay, so we can simplify this. Circuit. We can simplify it thus. Okay. So you can lump all of this. It's going to be 68, since they're in parallel, times 5. So basically you're going to have a 68 times 5. So you have a 340 microfarad equivalent. That's what this is. Basically you add these up. And then the ESR is going to be the 45 milli divided by that. So by 5. So 0.045 divided by 5. So the equivalent is 9 milli. Okay. So now We simplified it. So this is and this is 340 microfarads. So let's calculate what the ripple would be. Okay. So we're going to say that's 1 divided by 6.28 times 100 times 340 close. So the reactance is only 4.68 milliohms. Is that what I got? Yes. Okay. And it's in series with this. So now we can say V ripple 4 amps times 9 milli squared plus 4.68 milli squared. Okay. So let's do that. Let's do the impedance or the magnitude. It'd be 0.009 squared plus 0.00468 squared close raised to 0.5. So this is approximately 10.1 milli ohm is the, so you should have 40.4 millivolts peak to peak, or at least close. It's an approximation, of course. Okay, so let's do that. Okay. Let's simulate for a little longer since it's such a big capacitor. It takes longer to charge. Okay. Probably need to run it a little bit longer. Although the rip bar can probably measure that already. Let's go 20 milli. As you add more capacitor, it does take longer for it to reach steady state. So a lot of times when I need quick calculations, I do often reduce the value of the capacitance just to get cut down on the simulation time. But if you do want ripple, then you just gotta let it run. It might take a little while. So right here it's already taken over a minute. So it's almost there. Okay, so you notice reach steady state. Okay, so we'll zoom here. Okay, let's see what we get. Okay. So the delta. What we get? Okay, so we actually get a little bit better. So we got 36.8. 36.8. Okay. 36.8 millivolts peak to peak. So this is SPICE. This is hand calculation. Okay, so hopefully this will give you a little bit of an insight in that you want your capacitor as big as possible, okay, and that the ESR for the most part, provided that your capacitor is big enough, is what basically determines your ripple in most cases. Okay. Excuse me. Hopefully, if you have any questions, feel free to email me at my regular email account, or you can post your questions here on my YouTube channel. And hopefully this will give you, I guess, a little bit of an intuition of how to select your capacitors. Okay. Thank you for watching.